now the last step that we want to do is apply the limit n to infinity. So this is now comes an argument that is very often used in this path integrals. Probably mathematicians are not so happy with it. So what we observe is here we have this integral over, that thinks still of it as being a large vector in a 2 capital N minus 1 dimension space. And what we do is every such a vector gets some weight. And this weight is an exponential of some function. And this is like some phase vector of an exponential, and we have these different contributions. Now we see that there is one contribution here, which is Qn plus 1 minus Qn times Qn plus 1. So what we in principle have is like we can think of one vector defines just some arbitrary points on all these time slices. So this can be a very wild thing. So if we think of a vector in the way we thought, but think of it as a discretized path in phase space, then in principle this is like arbitrary wild path. Okay? But now comes the argument, which is the observation is, well, if coordinates, for example, are very far distant at different time slices, so we have the time slice at time n and time slice at n plus 1. Now if the coordinates, for example, are just going from one end of your space to the other, this will be a very large number. Okay? So what we have, and let's call if it jumps like from one end to the other, like consider vector where we have contribution where this jumps arbitrarily, this will be a very non-smooth path, okay? Because we widely jump from one instant to the next. So what we see is that these non-smooth or strongly fluctuating paths, they have always very large numbers which are exponentiated with a factor I. Okay, so we have some phase vectors which have very large numbers. So if we look at their contribution in the entire, like the contribution of such a vector to this entire high-dimensional integral, we see is that what we sum is just the exponential of very large numbers. Okay, so if you think of one phase vector, so this all lives on the unit circle in the complex plane, no? So we have exponential of some I, some real number here. So this would mean that we have, let's say, if we take a very wildly oscillating path, we have at some time slice a contribution from the vector at Qn, Pn, some given vector, and then Qn plus Pn plus 1. This is just another very large number. So if this is a number much larger than whatever 2 pi, this is like just saying, well, it's random. No, it's like just adding randomly phases. Okay? And this is then like the kind of argument that we always use is, well, if you just sum random numbers on the unit circle, you get some kind of cancellation also. If you just say, tell me like numbers between 10 and 1 million, and then we just take the exponential with I and we sum all of them, and we would sum all of, like if we have enough people, we just get 0. Okay? So this is like the argument that we want to use to say, well, we can think of it as paths in this discretized path in this phase space, but in the end what we see is that due to these strong oscillations, what should actually survive in these integrals are those paths which are not widely jumping around, which are in some sense smooth. Okay? Because then the phase is just smoothly varying as a function, so we just make small steps and we will get something finite. Okay, so it's like the hand-waving argument to argue the following. Okay, we have here an integral over discretized path, but what actually really contributes are in some sense smooth paths. So smooth here meaning that the vector, which is this very large vector with n depending from 1 to n, if we take this as a function xn of this time slice, this will be a function which smoothly varies as a function of this index. Okay? Now if this is a function that smoothly varies of this index, you can immediately recognize, oh, it makes sense to think of this in the limit delta t to 0 as some derivative. Now here, for example, if this is a smooth function, you don't really care if this is at coordinate or momentum n or n plus 1 because it's smooth, it only varies smoothly. So this allows us to make simplifications, okay? But it's an argument that we often like to use, and it makes sense because we arrive in an object, we can do calculation, which often makes sense. But if you talk to a mathematician, probably, actually I don't know, but I guess there by now what which accept it, but maybe some curious will say, well, I don't know what you're talking about. Okay, but this is the idea. Should I write down like what I said? No, should I write down what I just said, like with some keywords, or should I write down like a little?
I have another question regarding this first order approximation that you wrote in the beginning, the Bacon.
Yes.
Because if you take the first order approximation, it's equivalent to just assuming that the operators commute.
Yes.
Which is, let's say, a quantum hypothesis.
Yes, yes, yes.
But then you expect to get quantum effects.
Yes, yes. So the initial, so that's a good point because this really brings exactly what the path integral is about. So what you do is you somehow neglect like the essential thing of quantum mechanics, which is saying you're dealing with operators. You do exactly what you say. You have used Baker-Campbell-Hausdorff in the simplest approximation, saying you substitute an operator by some C number. So you forget about the essentials about quantum mechanics, so how should it work? The statement or the observation is, yes, we do it, but we do it at some price. We do it by introducing this time slice delta t, and we say that it only works if delta t becomes small. So if we accept, like using the step, we are forced to do something. We are forced, instead of talking about quantum mechanics, we talk about x and p. They're operators, but they're x and p. They're still describing quantum mechanics coordinate and momenta, like if you go to the eigen representation of a zero-dimensional object. So what we do is we exchange the operator for C numbers, but we do it at a price which is going from zero-dimensional to one-dimensional objects. So instead of looking at points in phase space, we now talk about trajectories. So the entire quantum mechanics then enters by taking, so we are forced to not consider time steps t because it doesn't make any sense. We are forced to consider small time steps. In the construction of the amplitude, we are forced to integrate then over the time slides, which leads us to trajectories. So this is like a deep connection, which is, if you have a quantum problem in d dimension, you can exchange it for some classical problem. Classical meaning exactly we're talking about trajectories, we're talking about phase vectors, numbers, there's no operators. So we exchange a d-dimensional quantum problem for, in a sense, a classical problem in one-dimensional higher. This just generalizes then exactly like the path integral to quantum field theory. Okay? So that's like a very nice different view of quantum mechanics, I think. It's like path integral. Talk about classical objects, but you're forced to go in one-dimensional higher. And then there's another connection. You can now think about like this weight, but I'll come to this, but just to make this one more connection, you can think by redefining here this time some way, you can think of this some just statistical weight. So what you integrate is over path, which has some statistical weight. So you have some connection, some sense to statistical physics. So your zero-dimensional quantum mechanics by the path integral becomes a one-dimensional object, and you can think about like the statistical properties of lines. Okay? So it's a very nice connection, which is okay. So I don't write down like what was said. I just now say like what is the continuum limit then. So that's the fourth and final step, the continuum limit. which now means sending n to infinity, which implies sending delta t to 0, but in a way that the time that we're interested in is fixed. So the product of n and delta t is fixed. Okay? So if we take this limit, we can substitute this factor that we, or this term that we over here, this becomes an integral over time variable t prime from 0 to t. Already mentioned, we can think of this then as a derivative of coordinate at some time t prime being tn. So tn is always defined as n times delta t. And we can exchange these numbers by v of q at a time t prime equals to tn. And here we actually have t of p at a time t prime, and there we can take the same time by the argument that we use that it doesn't make it a smooth variable, so it doesn't depend if you take n or n plus 1. And this actually then is what? This is the sum of the potential and the kinetic energy as a function of the classical coordinated momentum. So this is just the classical Hamilton function. So this defines the classical Hamilton function of a phase space coordinate at time t prime being tn. So that's a classical Hamilton function. Okay, so what I always use here is that I substituted just this, for example, or you can write x of n. Now I really write it as some x of t prime, okay? And t prime is now a continuous variable between 0 and t. Okay, so make the substitution, so to really have these trajectories. Okay, so this is just the formal steps, and then we can now do these steps here and see what we arrive at. Here we write it here. And what we then say is, well, if we take this smooth path, then also this delta t, order of delta t should not be really important, okay? This would be some function here of q, t of p, and so on, at some given coordinate. This shouldn't just diverge. So if you would allow for like derivatives or whatever, but this is proportional to delta t, and if you take the limit delta t to 0, you can forget about this. So if we do all the steps, we arrive at the goal that we had, which is the transition amplitude. Given in the following way. So I will define the notation. So we have some integral over path. So this will be the measure of integrals over path, which are paths given by some boundary condition. The q at time 0 is given by the conditional initial coordinate and q at time t and y final. And then what we integrate, so we integrate over all paths in phase space with this boundary condition, and each path has a weight which is given by the classical action associated with this phase space trajectory, because this turns out to be p times q dot with a plus, and this comes with a minus, and it's minus h. So we have p times q dot minus h, which defines the classical action. So with s, x is t, being the integral, p prime, p q dot minus h of classical action. Action associated to a given path. Okay, so just again, so this here is the classical Hamilton function, no? We said, and this here turns to p times q dot. So we arrive at this one here, which is the classical action. So should still define. Okay, I should have added here in the continuance limit just the definition, which is the definition of this magic here over integrals in phase space. So this is just defining the limit n to infinity of this high-dimensional integral r with the condition that q0 is q initial and qn is q final. This we define as measure okay, with q0 in q initial and q of t in q final. This is just in a way symbol now for us. If we don't know like how to calculate this, we can always in some way say, well, let's go to some discretized version where we can do integrals explicitly. Actually, that's the first example that we will do is to reproduce from this representation, now taking the free particle, just whatever you get from the simple calculation. This will be done in some discretized calculation. We just first highlight this expression here, because this is now our great result of this lecture, which is the path integral representation of the propagator or the transition amplitude. And just state again what it tells us. It tells us, well, to find the amplitude that particle propagates from some initial coordinate qi to a final coordinate qf in the time t, what you have to do is you have to sum over all possible paths. You can go in phase space, paths respecting the initial conditions, and what you should do is you should get every path you sum, you should give a weight which is given by the exponential of imaginary increment times the classical action associated with a given path divided by h bar. Now this is a very nice expression because, like, first of all, okay, it answers like the question that Dirac had when he asked, like, okay, so where's the classical action in quantum mechanics? So it turns out there's an alternative formulation of quantum mechanics, not based on operators, where you exchange operators at the cost of now looking at paths, and where the classical action appears very natural. So the question was a brilliant question, no? Because the answer is, well, there's a different interpretation of that. Now it tells you so what did I write here? Okay, so this just as like ask, like it tells you that well you can derive it in a representation where operators disappear, so you don't have any operators anymore, but you have a price to pay which is going from 0 dimension to 1 dimension object. Now it tells you also that there is actually, if you want to consider like this transition amplitude, what you should consider is all possible paths you can go. So all possible paths, I mean we still had some smoothness assumption, but what you should sum is all the possible paths, and we see that the contribution of paths gives is the weight where h bar enters as a natural like comparison scale for the action. And actually tells you also, this we'll discuss next lesson, is that, well, in classical mechanics we know that there is, like, classical mechanics can be formulated as variation of the principle, which tells you, well, there's very special paths, which, I mean, are the classical solutions, the solution of classical mechanics, are those which extremize this action. So this also can be seen as we discuss next class. So you have this integral over all possible paths, but actually there is a special class of paths which will be very relevant, which is the classical path extremizing this action. And actually, whether these classical paths become important or not depends on this ratio. So we should somehow see how from this formulation the classical word emerges. And I mean, there's already some suspicion. Well, here's clearly some signature of quantum, like a quantum scale, the quantum action. So if we consider actions that are much larger than h bar, this means somehow we are considering classical objects. Note the mass is very large. If you look at the distances much larger than the wavelengths of the particle, this is a very large scale. And this we discuss like next lecture. So the very nice thing is that it becomes immediately obviously here that then those paths extremizing the action become relevant. So from this expression you see that the classical path is the typical action associated with a given path connecting these coordinates is much larger than h bar. The classical paths play a distinguished role. So but just make some write down some things that I said. So the transition amplitude that we called star in the beginning, that we wanted to find, can be expressed in a form which does not contain operators. But an integral over path in classical phase space. Classical phase space. Then every path in this integral contributes, all the paths contribute to the weight. That is determined by the classical action. Associated with the given path is given path, and one thing said is that all possible paths, I mean there's some, again, all possible paths you should be always taking in mind. Well, we are still talking about really paths in the sense that they are smooth, no? So path doesn't mean like while talking about something continuous. Contribute not only towards those which extremize the action. But still, as said, if the typical action being much run in H bar, you will find that these play a special role. Okay, so this is like the thing that we wanted to do, derive an alternative representation for the transition amplitude. Questions or comments, or so now if you want to apply this machinery, of course you have to do a lot of integrals. So in the end, doing a lot of integrals will always reduce to some way to doing Gaussian integrals, because it's like the only thing that we know, so Gaussian integrals will be very important. So one should be aware of some identities for Gaussian integrals, so I can maybe just very briefly write down like very simple, just that you have like integrals that you will always use, and then we can finish. So just very small, like how you remind the Gaussian integrals. So in the simplest case, the 1D case, you're considering an integral dx e times this period dx, where a and b are real numbers. This is just given by so this will be like the one most important identity that you will use when working with function integrals. It always will boil to some kind of variation of this. So one.
Which is the first term in the
No,
the other way.
Here.
Q.
Oh,
Okay.
oh, so this is a half of times.
Okay.
Oh, sorry. No, oh, sorry.
Okay.
Yeah, thanks. Yeah, that was yeah. A half. Thanks. So this is the 1D case now. We thought about these path integrals at some point. This can always, if you don't really like to think about these objects here, you can still go back to some discretized version, and then you're talking about some high n-dimensional version. So let's call it the ND. N-dimensional. So here it's just a simple integral over R. So in an n-dimensional world you can think of a vector from the Rn. You can think of some matrix which is n by n. And we can introduce the measure of integrals over these vectors as just a product of these components. And okay, so this would be the measure, and then you can generalize this integral here as in the following way. So instead of integrating over numbers, you now integrate over these vectors. Here you have a symmetric form given by the scalar product, and you can have coupling of this vector to some other vector, which would be like in quantity theory, this could be some source. And this is just a generalization of so there should be some normalization factors like 2 pi. determinant to be 1/2, e to be 1/2, J transpose minus the summation from here. Okay, I hope one can read this. Okay, so this is just a generalization of this. If we put here n being 1, well then this is just this integral here. Okay? Now, if you like, you can think how to prove it. Well, you see here, this is, I wrote down a general matrix, but in the end only symmetric matrices will play a role because this is symmetric form. So you can think of different ways how to prove this. Should I read it out or is it visible? So V transpose A, V, and then you have some vector J of T times V, so the J would generalize to B. And this is the determinant of A to the minus 1/2, so this would correspond to 1/8 square root. So you can think of diagonalizing, for example, this A. So then this determinant would be just a product. So if you diagonalize this here, then you can like separate this in a product of individual integrals. What you will then have is always a product of 1 over the eigenvalue square root, which is the product of the eigenvalues is the determinant, so you get 1 over square root determinant. And then you would get b times x in this eigenvalue, so you can see you can write this as j t a times j. Okay, you can try to prove this. Now, what we are dealing with is actually functional integrals, where we want to generalize all this now, instead of having a high dimension, n-dimensional space, to some functions, okay? But if you don't like it, just always think about it in the end you can always think about it as some very fine discretization of some very large n, okay? But if you want to generalize this, you can talk about functional integrals, which is what we also declare, where which we will deal with. And there the formula for Gaussian integrals will then be the one into infinity. So what we will think of, so we generalized here from some number x to some vector mean r of n. Now taking into infinity, we can think of generalizing this vector component v of I to some function v of x. Okay, so instead of integrating over some large vectors, we integrate over functions. Now this matrix element Aij that defines here the quadratic form, then will also become a function which depends on two continuous variables x and x prime. And the measure which we introduced here, dv, in the limit n to infinity, is just the measure that we introduced as being d of x. Okay? So if you make these substitutions, we can generalize this, and I try to write it now in some more readable fashion. So this would be the functional integral over functions v of x, so functions which depend here on one coordinate. And what we want to integrate typically is some Gaussian weight, which is given by some quadratic form. So this is a scalar product for vectors. You can generalize this to scalar product of functions in function space, where the sum over the vector indices becomes an integral. Okay, so this would be v of x and v of x prime, and you multiply this by the matrix element x and x prime. This would just correspond to here v of I, a, I, j, v of j, the sum over I and j, comes integral v of x. And then, well, this here just becomes a scalar product. J of I, v of I will become an integral j of x, v of x. Okay? Okay, sorry, sometimes it's a little messy, but plus integral dx j j of x, p of x. Okay, so this will be the generalization of this. And this now, the integral, we get the determinant, the function determinant, a minus 1/2. So in most applications, we will still think of this then in the end as some matrix, because often you have some boundary conditions, so which will then lead to some discrete spectrum of this operator, and then this becomes just again the product of the eigenvalues. So we will example what this means, and then we get the generalization of this scalar product J of the source of the matrix J now becomes dx. I should have put here a to the minus 1, sorry. The inverse of the matrix. J of x, prime, J of x prime, and the inverse of this operator is here just defined by the definition of the inverse, that if you multiply this by generalization of the matrix multiplication, this gives you the identity of the multiplication. Okay? So this is inverse. Okay, so this is some generalization, continuum generalization of this, but if you don't like it too much, still think of this as some surprise. So this is like what we will always need to, what we will be using in the very end, like up to whatever. Yeah? Okay, so it's good to recall this identity. And maybe one very small remark still is here, what we actually have is the path integral in the Hamiltonian formulation, because we are talking here about integrals over phase space, and this is like the Hamiltonian is explicit. Now what we can do is, if you insert this expression here, you see you have an integral over p and over q. Q is fixed by the boundary conditions, this is like p squared or whatever. So this consists of a term p squared over 2m, which is a Gaussian weight for p, and then it's a function of q. Okay? So if we think about this integral, we can write this as a function integral over q of t times the function integral over p of t. The weights are e to the I over h bar. Now we have p squared over 2m, it's a Gaussian weight from momentum. Then we have a Gaussian, or then we have some weight by some potential e to the I over h bar v of q. And then we have a coupling between q and p, which is linear in the sense that it's p times q dot. So what we see is that the integral over p, if you just concentrate over the p content, it's integral over p squared times e times I p q dot. Okay? So there's still the issue that it's all here purely imaginary or whatever, but you can generalize these integrals which are there real to some complex. So what you can do, maybe just as an exercise, you can well apply this formulas for doing the integral over p, because it's just a simple Gaussian integral. So once you integrate over p, you should arrive at a theory purely in q. So this will be a path integral instead of an integral over phase space, just over coordinate space, which will depend on v of q, and some term which is introduced by this coupling of p and q. And what you should find is that you arrive at the Lagrangian formulation of the path integral, where again appears the action, but now the action expressed in terms of the Lagrangian. So this is maybe one exercise, maybe I write it down and give some exercise. But who, like more or less as an idea, can try to do it already or afterwards to discuss it. Okay. Yeah. So, just, eu nunca sei aqui com o tempo, então como é que funciona? A gente começa